Hi everyone, welcome back. In this lecture we're going to go over conditional probability and independence of events. Best way to do this, let's dive right into an example. So we're going to look at the set of binary sequences or binary strings of length 8. And then we're going to look at two events. The event A, which are the sequences that start with 3 ones, and event B, which are the sequences that contain exactly 5 ones. And then we're going to ask the question, suppose we pick a string from A at random. What is the probability that it is also in B? So let's collect together the information that we have. So we've got this sample space S, that's the set of all binary sequences of length 8. In that sample space, we've got an event A, and we've got another event B. And there could be some overlap in those events. Now, as an example, A is the set of sequences that start with 3 ones. What would be an example of that that isn't in B? Well, we could have 3 ones followed by 5 zeros. So 1, 2, 3, 4, 5 zeros. What would be an example of something that's in both A and B? Well, it would have to start with 3 ones, and then it would have to have 5 ones in total. So maybe 3 ones and a 0, 1, 0, 1. How many characters in that? That's 3, 4, 5, 6, 7, and then followed by another 0. So there's an example of something that's in both A and B. Something that's in B alone, so maybe 0, 1, 0, 1, 0, 1. So that's 1, 2, 3, 4, 5, 6, 7, 8. So there's a string with exactly 5 ones, and it doesn't start with 3 ones, so it's not in A, but it is in B. So there's some examples, and then maybe I have the 0 sequence. So 1, 2, 3, 4, 5, 6, 7, 8, etc. So there's just some examples of some of the strings and where they would sit. What we are interested in is what if we pick a string from A. So I pick a string from set A. Maybe I'll circle or draw A with this yellow boundary on it. So from that set there, I pick an element. I want to know what's the probability that it's also in B. So what's the probability it's in that shaded region? So picking from A, what's the probability it's in B as well? Now you may look at this and just say immediately, oh, I know what that is. It's the size of the successes, the space of successes, so the events that I want to consider successes. And so those would be the things that are in the intersection of A and B, divided by the possible choices I had. And that was the size of the set A. So it's the size of the intersection over the size of A. Perfectly correct. That's exactly what we want to get to. I am going to get to there, though, by just listing out all of the ingredients that we have. So I will list out the sizes of each of the event spaces and then bring it all together. So what are our event spaces? Well, we've got the sample space, S. This is a set of all binary sequences of length 8. So we know that there are 2 to the 8 of them. What's the size of our set A, our event A? Those are the sequences that start 1, 1, 1. So the remaining 5 digits can be any of 0s and 1s. So of those 5 spots, there's 2 choices for each. So the size of A is 2 to the 5. What about B? B consists of those strings of length 8 with exactly 5 ones. So we know what those are. Of the 8 choices, pick 5 of them to be the 1s. The rest can be the 0s, and so that's the size of B. What about A intersect B? We'd like to know that because that's the shaded region in our diagram, or at least the overlapping region. So that is the set of all sequences that start with 3 ones, and then the remaining bits, so the BIs, could be anything from 0 and 1, and we want it to have, and has exactly 5 ones. So that's our intersection. How big is it? Well, if it's to have exactly 5 ones, it means that in those digits B4 to B8, exactly 2 of them have to be 1, because we've already used up 3 ones. So of those 5 remaining spots, exactly 2 of them have to be 1s, and the rest are 0s, so we get our 5 choose 2 there. And now a little bit of notation. We'll let PR of B with a vertical bar A, and that vertical bar we can read as given. So the way we'll read this is the probability of B given A. In other words, the probability that our outcome is in B, given that we already know it's in A. This is what we're interested in. So let PR B given A be the probability the outcome is in B, given that it is already in A, then that's what we're trying to find. What is this probability? So the way we can do this is we can just say, well, if I already know that the string that I selected is in A, then I'll just treat A as my sample space. So forget about all of S, just focus in on A. A is my sample space. So if I pick something from A, what's the probability that it's also in B? Well, it's the probability that it is in the intersection of A and B. So select something from A, what's the probability it's in B? It's really just select something from A, what's the probability it's in A intersect B? So it's the size of the intersection of A and B all over the size of A, because now I'm thinking of A as my sample space. The size of A intersect B, that's 5 choose 2. The size of A, that's 2 to the 5. 5 choose 2 is 10. 2 to the 5 is 32. Both of those are even, so I get a 5/16. So the probability that if I've selected a string and it is from A, the probability that it's also in B is 5/16. Now I'm going to add one more thing here. So we just did it by regular counting. Just what's the probability of your selection from A is also in B? It is the size of your intersection, where your successes are. That's that double shaded region in the diagram, A intersect B, divided by the possible outcomes. And the possible outcomes in this case were from A. How else could we look at this? Well, I could look at this expression here and just write it as A intersect B, and I'll bring the larger sample space into the mix, over S, and then A over the size of S. So I just inserted a division by S in the top and in the bottom. So I multiplied by 1 in a fancy way. And this becomes the probability then of A intersect B all over the probability of A. So that's just another way to view it. Instead of viewing it as the size of sets, we can view the probability of B given A as the ratio of two probabilities, the probability of the intersection over the probability of A. And that gives rise to our next definition. This is known as conditional probability. So if S is the sample space and A and B are two events, then the conditional probability of B, given or knowing that A has already occurred, is denoted by PR of B with the vertical bar and then the A following it. And that is the probability that a random outcome from A also belongs to the event B. And as we've just verified, it can be obtained by the formula. Probability of B given A is equal to the probability of B intersect A over the probability of A. Now we didn't verify this in general, but this is a definition. So we don't have to verify a definition. A definition is a definition. It's just a statement of what the conditional probability is. But we have motivated this definition through our previous example. So let's have a look at this next example. Assume 2 dice are rolled. What is the probability that if they sum up to at least 9, we'll call that event A, that both dice have the same value? We'll call that event B. Now this is where I really encourage you to write down the sample space, its size, the events and their sizes, so that everything is right there. All the ingredients we have to work out various probabilities is all right there in front of us. Even if this is something that you can just quickly look at and maybe off the top of your head you can say what it is, I do encourage you to write down the events. It will make more difficult situations involving probability much more straightforward to deal with if we are able to think in terms of these sets. So what are our sets that we're interested in? So we've got our sample space S. So our sample space is the set of all die rolling pairs. So the values that can come up on die 1 and die 2. So DI, they're going to be values from 1 to 6. We're imagining it's a standard 6-sided die with values 1 through 6 on the sides. So that's our sample space S. It has size 36. What is event A? Event A is that the sum of the die rolls is at least 9. So what that tells us is it's the set of all pairs in S such that D1 plus D2 is at least 9. What is that as a set? I mean, we're going to want to count this, so maybe we'll just list it out and then figure out how many elements there are. So if the sum is to be at least 9, then we know that one of the dies has to have size 3 or more. So maybe we'll start that as the die 1. Die 1 could have 3. And then therefore die 2 would have to have 6. Couldn't have 5 because that sum would be 8. So it has to have at least 6. And that's the biggest number it'll have. So then what's next? Well, our first die could be a 4. And if it's a 4, then the other one could be a 5 or a 6. Or the first die could be a 5. And the other one could be a 4. Or it could be a 5. Or it could be a 6. Or our first die could be a 6, in which case the second die could be a 3, a 4, a 5, or a 6. And those are all the possibilities we have for the sum of two dies to be at least 9. What's our next event? Our next event is we want both die to have the same value. Okay, so this would be, like a D, D, such that D is in 1 through 6. So that's event B. Now, what is A intersect B? Because we're going to need to know that. A intersect B. Well, those are all the pairs that we can get with a die roll for which the sum is at least 9 and we get the same value on each die. So I look at the event A and I pick off the ones which also live in B. And they are those two. So this is going to be 5, 5 and 6, 6. And so the size of A intersect B is 2. Maybe I can add these other ones here. The size of B is 6. And the size of A is, we can count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is 10. So now we've got all our ingredients. We are interested in what is the probability that B occurs given that A has already occurred. So given that the sum is at least 9, what's the probability that the value is the same? That's the probability of A intersect B all over the probability of A. And that is the size of the intersection over the size of S over the size of A over the size of S. We could cancel out the size of S in each case and just work with the size of the sets rather than the ratio of the probabilities. What's the size of A intersect B? We worked that out to be 2. What's the size of A? That worked out to be 10. So the result is 1/5. Or, in other words, 20%. So 20% of the die rolls that sum to at least 9 will have the exact same value on each die. So let's have a look at 4 consequences of conditional probability. So again, the conditional probability formula is there. Probability of B given A is the probability of their intersection divided by the probability of A. We can switch the roles of A and B in this formula. A and B were just 2 events, so I could switch their roles. And what I get is that the probability of A given B is equal to the probability of A intersect B all over the probability of B. The nice thing about this is they have something in common. The probability of B intersect A, probability of A intersect B, those are the same because A intersect B is B intersect A. And so what I can do is I can solve these 2 equations for the probability of their intersection. And that means that the probability of A times the probability of B given A, so that is taking the equation at the top of the page and just multiplying both sides by the probability of A, that's equal to the probability of the intersection. But the second equation on the page, we could multiply through by the probability of B, and we get that that's also equal to the probability of B times the probability of A given B. And this is known as the multiplicative rule. It expresses the probability of the intersection in terms of 2 conditional probabilities, either the probability of B given A or the probability of A given B. Now we can use this multiplicative rule to get to further results. So the law of total probability. If we take our event B and write it as the union of 2 disjoint events, so I will write it as B intersect A union B intersect the complement of A. This is a disjoint union. They have nothing in common. So that means I can work out the probability as just the sum of the 2 probabilities. And the nice thing about this is we now have an expression for the probability of an intersection as the product in terms of conditional probability. So the probability of B intersect A, that's the probability of A times the probability of B given A, plus the probability of the complement of A times the probability of B given the complement of A. And so this expression for the probability of B as the sum of 2 probabilities is known as the law of total probability. And you might not see how useful it is right at this moment, but I hope in the next example I'll show you that this actually turns out to be quite useful. It allows us to work out the probability of B given that we know some conditional probabilities about B in its relationship to A. So the last thing we can do is we can take this equation up here and just eliminate the probability of the intersection from it and just focus on the fact that the left side, the probability of A times the probability of B given A, is equal to the expression on the far right, which is the probability of B times the probability of A given B. Now, if we go ahead and solve for the probability of B given A by just dividing both sides by the probability of A, then what we get is that it's equal to the probability of B times the probability of A given B divided by the probability of A. And this is known as Bayes' theorem. What it does is it relates 2 conditional probabilities. The probability of event B occurring, given that we know A has already occurred, as compared to the probability of A occurring, given that we know B has already occurred. And this is the relationship between those 2 conditional probabilities. Now, it turns out that this is quite important for a lot of applications, and we're going to look at one next involving testing for drugs. So any kind of testing, testing for diseases, testing for drugs, there are relationships to conditional probabilities that come up, and we need to be specific as to which conditional probability we are interested in, which one we know about, which one we are interested in, and Bayes' theorem will give us the relationship between the two. So let's have a look at that. So we're going to suppose, in this hypothetical situation, that 10% of Olympic cyclists use a particular steroid called Z. So these are all made up numbers, but this is just to illustrate how these kinds of ideas get used. So the IOC has developed a test for Z with the following properties. If a cyclist is taking Z, the probability they test positive is 0.99 or 99%. If they are not taking the steroid, the probability they test positive is 0.05 or 5%. So this is known as a false positive. So it has a 5% false positive rating. Now, we want to know if a randomly chosen cyclist tests positive for Z. What is the probability that they are actually taking it? So they test positive. What's the probability they're actually taking it? Now, you might think back around Olympics time. This is often something that gets reported quite a bit in the media. Such and such an athlete has tested positive for a drug, and almost immediately it's like they're guilty. But what we're going to illustrate here is that we shouldn't be so quick to judge guilt based on the fact that someone has tested positive. In fact, I'm going to let you make a decision right now. You read this or you hear about it on the news. Someone has tested positive for taking a steroid. And how likely do you think it is that they are taking it? Would you be 99% certain they're taking it, 95% certain, 90% certain? How high should our certainty be? And that's what we're going to calculate. And the result may surprise you. So let's collect together our ingredients. So we have our sample space. So this is going to be the set of all Olympic cyclists. And what's next? Well, we're going to have our event A. So we are interested in whether they're taking it and how they test. So we'll let A be the cyclists that are taking this steroid Z. And then our event B is going to be about their testing. So this will be the cyclists that test positive. So cyclists test positive for Z. And what are the things we know? So we're given a few things in the question. So a couple of things we know. We know that the probability of A, we are assuming that 10% of cyclists use steroid Z. So the probability of A, that a person selected from our sample space actually is taking the drug. That's 10% or 0.1. What else do we know? Well, we know that if a cyclist is taking Z, then the probability they test positive is 99%. So that is, if they are taking Z, so that's given A, what's the probability they test positive, or the probability of B? That's 0.99. What else do we know? We know that the probability that they test positive, given that they aren't taking it, so this is the false positive, that's 0.05. So those are values we know. What do we want to know? Well, what we want to know is if a randomly chosen cyclist tests positive for Z, so that means if they are in event B, what is the probability they are also in A, that they are actually taking it? So we want to know what is the probability that, given they test positive, they are actually taking it? So how do we get that? Well, by Bayes' theorem, the probability of A given B, we want to relate it back to things we know. So let's look at our known line. Probability of A, probability of B given A, probability of B given not A. Probability of A given B, by Bayes' theorem, that's the probability of A times the probability of B given A all over the probability of B. So that's, I'll put BT up here for Bayes' theorem. Now, I know the two probabilities in the numerator. I don't know the denominator, but that's all right, because even though I don't know what the probability of B is, I do know what the probability of B given A and given the complement of A are. And so I can use the law of total probability to get that the probability of B is the probability of A times the probability of B given A plus the probability of the complement of A times the probability of B given the complement of A. So this is by the law of total probability. And now I have all of those values. Probability of A, that's 0.1. Probability of B given A, that's 0.99. Probability of A, again, 0.1. Probability of B given A, 0.99, plus the probability of the complement of A. Well, the probability of the complement of A is exactly 1 minus the probability of A. So this is going to be 1 minus 10%, or in other words, 0.9. And that's times the probability of B given the complement of A, which is 0.05. And with all those values, we can work it out, and we get the answer of 0.6875, or about 69%. So the probability a randomly chosen cyclist had tested positive, the probability that they're actually using the drug is about 69%. And that is really low. Really low to make a definitive decision that says, yes, you were taking it and you're kicked out of the event. 69% chance of being certain that they are taking it based on that positive test? That's too low. Was that surprising? Did that surprise you? I mean, you might think about, you hear these things in the news all the time, but here's an example of some numbers and how they shake out in the end. All right, let's have a look at the next topic, which is independent events. So two events, A and B, are independent if either one of them has probability 0, or if they both have positive probability, then the probability of B given A is the probability of B, and the probability of A given B is the probability of A. So the idea we're trying to capture here is that two events are independent if their probabilities are really independent of each other. And so what does that mean? It means that, you know, this last line says that the probability that event B is occurring, given that we know A has already occurred, well, it really makes no difference whether A occurred or not, because it's just the probability of B occurring. And that's what we're trying to capture with this independence. It turns out that these two equations, if either one of them is true, the other one is true. So if one is true, so is the other. And the reason is if the probability of B given A is equal to the probability of B, then the other equation has to be true as well. That's just Bayes' theorem. So we look back to Bayes' theorem, it's really saying, you know, if the probability of A given B is equal to the probability of A, then those would cancel off, and we'd get the probability of B given A is equal to the probability of B. So it's really just a consequence of Bayes' theorem that only one of those equations has to be true in the definition. We've stated both because this means that you could really check either one of them and get independence that way. So for example, what does it mean to be independent? Well, if we toss a coin twice, the outcome of the coin on the second flip is going to be independent of what happened on the first flip. It makes no difference. If I tossed a head on the first flip, that's going to have no indication as to what the outcome is going to be for the second flip. That's what we mean by the events being independent. One has no influence on the other. So the resulting theorem, which follows from the definition, and we'll prove it, is that two events are independent if and only if the probability of their intersection is the product of their probabilities. Now, this is just another way to phrase independence without having to use conditional probabilities in the statement. The definition uses conditional probabilities. This theorem uses intersections instead. By the way, this theorem is what Grimaldi takes as a definition of independence in the textbook. So he uses this probability of the intersection is the product of the probabilities as the definition of independence, and then would get what is our definition as a result. But we've chosen to go with the conditional probability definition first, and then we'll prove this intersection property from it. So how do we prove this intersection property from it? Well, suppose A and B are independent. Well, that implies then that the probability of B given A is equal to the probability of B. That's by the definition. And I'm only going to use one of the equations in the definition because, as I said, if one of them is true, so is the other. Now what we're going to do with this equation is we'll multiply it by the probability of A. So I'll multiply probability of A to both sides. And I get this expression. And now I note that the probability of A times the probability of B given A, that is the probability of their intersection. A intersect B. And that's really just the definition of conditional probability. The probability of B given A is the probability of their intersection over the probability of A. So we just reworked it and rewrote it in this way. And that's the probability of A times the probability of B. And so we have proven that if they are independent, then the probability of the intersection is the product of the probabilities. On the other hand, if the probability of the intersection is the product of the probabilities, then we can reverse all of these implications. Then I can rewrite what the probability of the intersection is in terms of conditional probabilities. I can divide both sides by the probability of A and get the expression that is the definition of independence. So just working those implications in the opposite direction, we get the equivalence there. And so that's the if and only if part of the theorem. If they're independent, the equation is true. If the equation is true, then they're independent. So let's go ahead and do an example where we want to check if certain events are independent. So here we've got Alex tossing a fair coin 3 times, and the resulting sample space is given there. There's 8 possible outcomes. Consider the events. The first toss is a head. So there we've got 4 possible outcomes, all beginning with an H. Event B is the second toss is a head. So there are the 4 possible outcomes where the middle toss is an H. And the last event is there are 2 or 3 heads in the toss. So what do we have for values here? We have that the size of A is 4. And so in this case, the probability of A is the size of A over the sample space. The size of our sample space is 8. So that would be 4 over 8, or a half. And similarly for all the other ones, because they're all of size 4 as well. The probability of B is a half. The probability of event C is a half. I want to know, are A and B independent? So this is a question as to whether is the probability of their intersection, so I'm going to use the theorem on the previous page, is their intersection, the probability of their intersection, equal to the product of the probabilities? If it is, they're independent. If it isn't, they are dependent. This side we can work out. It's a half times a half, or a quarter, just using our values above. What about A intersect B? Well, A intersect B, that is the set of all outcomes where the first toss is an H and the second toss is an H. So they start heads, heads. Then for the third toss, it could be an H, or it could be a T. And so in that case, what is the probability of the intersection? It's the size of the intersection over the size of S, which is 2 over 8, or a quarter. And those are equal. So the answer is yes. That's a equality, and therefore A and B are independent. How about are A and C independent? Well, again, that's asking the question, is the probability of A intersects C equal to the probability of A times the probability of C? Again, this side is a half times a half, or a quarter. What's the probability of A intersects C? Well, we can work out what the intersection is. A intersects C. So those are all the things that are in C, but also in A. So I'm looking at C and saying, what are the ones that start with an H? Well, the first three do. So there's H, 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 T, and H, T, H. And so there's three of them. So this is going to be 3 over 8. And that is not the same as a quarter. So those are not equal. So this is a no. A and B are dependent. And how about the last one? Is the probability of A intersect the complement of A equal to the probability of A times the probability of B complement? And these were question marks here. What is this side? Well, the probability of A is a half. What's the probability of the complement of B? Well, it's 1 minus the probability of B. That's 1 minus a half, so it's also a half. So again, this is a quarter. What is A intersect B complement? So those are all the things that start with an H, but the second toss is not an H. So they would go HT. So it would be HTH or HTT. So it's 2. So this is equal to 2 over 8 or a quarter. And those are equal. That is equal to that. So the answer is yes. A and the complement of B are independent. And so we can think about, why they should be independent. So A and B, if the first toss is ahead and B is the second toss is ahead, are they independent of each other? Yeah, really the value of the second toss has nothing to do with what the value of the first toss is. So they should be independent. How about A and C? Well, A is the first toss is ahead. C was there are 2 or 3 heads. Well, in that case, if your first toss is ahead, now you've got 2 tosses left, and you're trying to get 2 or 3 heads. So you're already making some progress there. And so there's some dependency between, satisfying the conditions of event C and satisfying the conditions of event A. You're already part way to satisfying all the conditions of C if you've already satisfied A. So there is some dependence there. How about A and B complement? Well, again, one is about the first toss, the other one is about what's happening on the second toss. They have no influence on each other, so they are independent. All right, so that's it for this section. Thanks very much for watching, and we'll see you again next time.